So yesterday I gave the definition of finite perimeter set, some examples showing that this class includes many things, but also includes some unpleasant things. And this is due to the fact that it is defined just with the goal of getting easy compactness results. So I will start now with giving some properties of finite perimeter sets. And the first one are the properties which are important but easy to prove because essentially comes from functional analysis, okay? And so the first property and finite perimeter sets. The first property is the semi-continuity of the perimeter. Okay, now remember that somehow the approach we have in mind is based on semi-continuity and compactness to get existence results, and that the perimeter is the replacement of the area of a surface, or more precisely, the perimeter of a set is the right replacement for the area of the boundary of the set, okay? And so the first thing is we want to show semi-continuity of this quantity, okay? And so this is it. What is the statement is that this function is lower semi-continuous with respect, for instance, convergence in L1 lock. Convergence in L1 lock. When I say convergence in L1 lock, talking about sets, I'm talking about the convergence of the characteristic function, okay? And how is it so? So that is, in other words, we have to prove the following, that if En converges to E, well, the characteristic function, say, in L1 lock, then you have that the limit of the perimeter of En as n goes to infinity is larger or equal than the perimeter of E. And the proof is immediate from the definition of perimeter. Okay, so that was our constraint. We take the perimeter, we take the supremum of this divergence among all smooth, compactly supported vector fields which are less than 1 everywhere in supremum norm. But now, what does that mean? It means that we have to define the perimeter. So this map, this function, sorry, is the pointwise supremum of the following maps. And now this function, sorry, I say maps, functions. This function is clearly continuous with respect to L1 lock convergence of sets, obviously. So this function has been written as a supremum of a family of continuous functions, therefore it's lower semi-continuous. Okay. So, and these are, which are L1 lock, lower semi-continuous. Okay, so that's how the perimeter is defined and makes it naturally lower semi-continuous. Notice that I didn't, I think I mentioned it, the Hausdorff measure is not lower semi-continuous with respect to any type of convergence. So that doesn't happen with the Hausdorff measure of the boundary, of the topological boundary. Okay, so it happens for the perimeter, not with the Hausdorff measure of topological boundary. Okay, so remark. With respect to any reasonable convergence. So there is something better about the perimeter than the Hausdorff measure of the topological boundary. Okay? And, okay, so this is the first property. And the second one is, okay, semi-continuity. The second is compactness. So the statement is the following. If you have a countable family, well, maybe n is the dimension of the space. So if you have a countable family, a sequence, finite perimeter sets in Rn, and you have some assumption. So the first is that they are uniformly bounded. Well, let's say contained in a ball. And the second is that the perimeters are uniformly bounded. Well, then you have compactness. Up to there is a subsequence which converges in L1. Then, up to subsequence, EI converges to some E in L1, and E has finite perimeter. Well, this last property is a corollary of the semi-continuity, right? If these are uniformly bounded, then this has to be finite as well. Okay, so the point is, and now it's clear that in some sense these are exactly the properties we wanted to apply a direct method in some sense. Okay, so this is the basic, and also this one is an easy statement. Well, doesn't matter too much. Okay, let me say, maybe this was not a brilliant idea, but okay, I apologize. But okay, how comes, where do I get compactness from? Well, the fact is that under those assumptions over there, these functions this sequence of functions is bounded in the space BV. Okay, this was not mentioned till this moment. What is BV? BV of some omega, of some domain omega, is a notion which is similar to that of Sobolev function, and is the space of U in L1 such that the distributional derivative is a measure. Okay? So clearly finite characteristic function of finite perimeter sets by definition are a subset of this. Okay? And now this is actually, if you want, the right if you want, is the right limit of Sobolev spaces W1P as P goes to 1. W11 is a nice Sobolev space but lacks compactness property. This one has the right compactness property. Okay, and okay, so if you look in standard books, maybe on Sobolev spaces, it is sometimes mentioned that when you go to P equal 1, the space with the nice properties is no longer W11, which doesn't have the good compactness properties because of lack of reflexivity, but it's this one, okay? And so I don't want to make a theory about this, but what is the key point here? The key point here is that this space embeds compactly in L1. Well, because Sobolev spaces embeds compactly. W1P Sobolev spaces embeds compactly in LP. So BV omega embeds compactly in L1 of omega. And that's what we are going to use. Okay? So we use compactness coming from Sobolev embedding. How you prove it for Sobolev for BV function, you prove it exactly in the same way as Sobolev function. So there is actually no difference. In fact, you can take the statement for W11 and in some sense extend it to BV by continuity. Not exactly, okay, you have to work a little bit, but this is nothing more than the standard Sobolev embedding, okay? So, of course, it's an important theorem, but I'm saying this is a theorem which relies on, I would say, standard functional analysis type of properties, and so I'm not particularly, I'm not going into the details. I somehow assume that this is so more familiar to people, and so I don't want to spend time on this compact embedding, but that's all you need. Okay, so this sequence is bounded in BV, therefore it's compact in L1. Okay, and therefore compact in L1. Okay, maybe you want to be a little bit careful about exactly which BV and which L1, because in some sense so far I didn't use. So what assumption did I use on this set EI that I said they must have finite perimeter? This is part of being compact in BV, but then I also assumed that they are uniformly bounded. And the reason I do that, if you want to be careful about this compactness embedding, you usually need that the domain omega is not Rn, but it's a bounded set. Okay, so let's say all these sets are contained in a ball of radius R. Well, then I will use the compactness. Just to be on the safe side, I will use this one. Okay? But this is just to be extra careful. I mean, it's not. So it's just a detail. Okay? But of course, I mean, if you don't put some assumptions on like boundedness, you could have a sequence of sets that simply escapes to infinity in Rn. So you do need some boundedness to have a compactness, okay? Otherwise, your sets could simply move to infinity and disappear, okay? Okay, so this is the proof of compactness. Let me mention that I need, in the following, I need a variant of this result, which I will write down here. So local version of compactness let's say you have a sequence of finite of sets which are have locally finite perimeter. If you don't, if you wonder what locally finite perimeter means, well, okay, means that the derivative measure is locally finite. And if you don't feel comfortable, just think about finite perimeter sets, okay? But it applies. So if EI is a sequence of sets with locally finite perimeter in Rn, well, then up to subsequence, they converge in L1 log to a set with locally finite perimeter. Then up to subsequence, in L1 log of Rn. And, oh, sorry. No, this is really crazy. I'm forgetting the assumption. Forget about this. There is an assumption. And the assumption is that the perimeter is locally bounded. Sorry, of course, it couldn't be that nice. So the perimeter is locally bounded. Now I want to talk about the perimeter of the sets, not on the entire space, but on subsets. And so I would like to say this is the perimeter of EI in the open set U. And what it is, well, if you want, you can define in many ways, but one of the ways is that you take this measure, you take it as a positive measure, throw away the vector part, and then compute this on the open set U. Or equivalently, you take the supremum of divergence of phi on EI, and here you ask that phi is less or equal than 1, and that phi is supported in U. Okay, so I don't want to use the local notion of perimeter too much, so I just mention it here. But of course, here I need it. So let's say that you know that this is bounded by some constant depending on U for every U open. Okay, then up to subsequence, these sets converge to a set of locally finite perimeter in L1 lock. Has locally finite perimeter. Okay. Yeah.
I need to see the difference between the two assumptions.
There is only one assumption. What do you mean?
Oh, no, that's not it.
Oh, this is a definition of what do I mean by perimeter of inside U.
Okay, no, it was the end. Sorry.
No, sorry. There is one assumption. You only ask that the perimeter is locally bounded. But then I have to say, okay, what is the perimeter of a set restricted to an open set U? Okay, I said so far I only defined the perimeter on the entire space. Okay, and so now I just wanted to say, okay, what is this perimeter within U? Okay, that's it. And this is the definition of perimeter within U, which you might have guessed. Okay, I agree. I mean, that's so there is only one assumption, is this one. Okay. Okay, I wrote this just because I need it. Okay, so far I gave existence, semi-continuity, compactness, and then the other theorem you really would like to have and the other easy theorem you really would like to have to make the theory complete is approximation. So you like to be sure that in some sense your finite perimeter sets can be approximated by smooth ones. Otherwise you might have created a space which is simply too large. Okay, so you create a space of objects which is where smooth objects are not dense, then you might start wondering whether you didn't enlarge your original space too much. In the moment you prove that dense regular objects are dense, in some sense you know that you didn't enlarge the space too much. So here it is, approximation. Okay. If E has finite perimeter in Rn, and finite measure, then we can find a sequence of smooth sets that approximate this set in L1. Okay, so the measure of the Lebesgue measure of symmetric difference goes to 0, and of course the perimeter approximate the perimeter. And the perimeter of these sets, EI, which happens to be, in this case they are smooth, the measure of the boundary, converges exactly to the perimeter of E. And you could be more precise, actually. But let's put it between brackets. Well, not only the masses of the measured derivatives converge, but in fact, the derivatives converge. Okay, in the sense of measures. And okay, and in fact, this is a convergence of vector measure, but even the corresponding positive measure converge. But I remind you, this is simply Hn minus 1 restricted to the boundary, while this is the measure we call mu, okay, which we don't know yet. That is H1 restricted to a rectifiable set. That's what we are going to prove next. Okay. By the way, again, for instance, this convergence is obvious. Again, that's part of the theory of distribution. Whenever some distribution converge to another sequence of distribution converge, then all derivatives converge as well. Okay. So that's a very immensely general fact. This requires a little bit of, is not general functional analysis, because it's not true that if you take vector measures that converge, when you pass to the positive measure, they converge as well. There could be cancellation, so to speak, in the vector measures that somehow shows that the limit of the positive measure is different. But in this case, it's not like that, and if you want, the key point is that when you go from here to here, you don't have semi-continuity, but you have continuity. You don't have loss of mass. Okay, so it's a technical detail. It's mostly, some easy fact about measures. Okay, so convergence of measures. I'm not going to spend time, but let me tell you how do you find this. How do you find this approximation? Because it's simple. Okay, so you smooth using convolution. Well, okay, so we take a sequence of smoothing kernels right. Take ui being the convolution of the characteristic function of E. Okay, these are smooth function. Sorry. Okay, but of course, now we are not finished. This is the standard way you regularize, you approximate function in Sobolev spaces by convolution. It doesn't work here because this is a very smooth function, but it's not a characteristic function, okay? But then what would you do? You would take a level set of this, okay? So for every s in 0, 1, sorry, maybe 0 and 1 you want to exclude, so you take this level set so what we are doing, essentially what is the scheme you're doing, okay, in one dimension, here is the characteristic function of your set E. Well, when you smooth it by convolution, you will still get a function with values between 0 and 1. That would be ui. And now when you fixed some value, so here is 1, some value s, here, you are taking this set here as EIS, okay? And, okay, now the idea is that if you choose Si carefully, depending on I, then you get your results, okay? So, so a careful choice of Si will ensure that these sets are smooth and converge to E as required. Okay? So what do you have to use to prove this? So I'm giving you the tools, but I'm not giving the details. So what you have to use, well, first you have to use Sartre theorem, which tells you that for almost every S, this set E Si is smooth, has smooth boundary. So first you use this, is smooth, well, has smooth boundary for almost every S in 0, 1 by Sartre theorem. Okay? Of course, I mean, if you are unlucky and you cut on at the wrong height, you may get a crazy set, but not if you take a random height. The second thing is you might want to use is something that relates this distance between this set and the set E to the distance between ui and u. Okay? So why should these sets converge to E? Well, one would say, well, because we know this function converged to the characteristic function of E in L1, Okay, so that we certainly have to use. Okay, this is standard fact about convolution of L1 function. But then you want to know, okay, yes, but what about the characteristic function? And you know this, okay, this is an inequality you can check. At the distance, if you look at the two characteristic function, at a point, so I'm giving you a pointwise inequality, this is less or equal than 1 over the infimum of S, the minimum of S, and 1 minus S, times the difference of ui of x and 1 of ex. Sorry, I'm messing up, but okay, you go there and check. You get this inequality. It's nothing.
So that's the
Min. 1 minus S. Sorry, what else is wrong?
EI that's on the left side.
Right. There is no such a thing as EI so far. Okay? So this is telling you that these two characteristic functions are close in L1. Well, not too, depends on where you choose S. If you get too close to 0 or to 1, then they are not that close. I mean, so this estimate gets worse as S goes close to 0 and 1. So you might want to avoid 0 and 1, or to stay close to 0 and 1. But as long as you do that, or you play, and that's part of choosing SI carefully, then you get. And then the last fact that you might want to use is the following, is the coarea formula. Which I didn't mention so far. It was supposed to be mentioned in my course, but it didn't happen, sorry. So, and it simply says in these specific things that the integral of the derivative of u, which is a smooth function, by the way, remember, is equal to the integral from 0 to 1 of the perimeters of it, of the set EIS. Or if you want, okay, or if you want here, you can put, since it's a smooth function, you can put the measure of the level set of U. Okay, so this is true for every function, which is smooth, and with values between 0 and 1. Okay, but now this converges to the perimeter of E. Why? Well, because this should converge to, that's again, here we have ui, the derivative of ui is the convolution of the derivative of the characteristic function of E times rho I. So whenever I take a measure and I take a regularization by convolution, they converge in mass. Okay? So if I take a measure mu and I take the convolution by rho I, they converge in mass. And so this is exactly the convolution of the characteristic function of the derivative of the characteristic function of E. Okay? So they converge in mass to the derivative of the characteristic function of E. And what is the mass of the derivative of the characteristic function of E is the perimeter. So if you have this, then you realize suddenly, okay, they converge to this. You don't know for a given S what these do exactly, but you know that in some sense here is an average. Okay, so let's put this way. For some S, this perimeter should be close to this. Or in fact, even less. I mean, if you are lucky, here there will be values which are larger than this. There will be values which are less because the average is exactly the same. So at least for some S, since the average of this function of these values is exactly is this number, for some s you must be below, well, or not too much above. Okay? So this is telling you that the perimeter of this set is not too far, if you choose S properly, is not larger than this, which in turn converge to this. So you have to use this. Okay? It's the only thing that tells you that these perimeters are not too huge. Okay. So, and I would say that if you are willing to work out the details, is just, I mean, you might have to be careful, but there is not much to say. Okay, and now we arrive to the last theorem. So I proved compactness, semi-continuity, and approximation. The things which is somehow missing is the part I mentioned yesterday, saying that, yeah, this measure here, it's actually not just an abstract measure, but it's really Hn minus 1 on a rectifiable set, making somehow the boundary of this set something which you would consider an acceptable n minus 1 surface, dimensional surface. Okay, so this is the hard part. So far, what I told you is rather elementary, based essentially on functional analysis, or what we know of Sobolev spaces, doesn't use anything specific of geometric measure theory. But the next result is the hard part of the theory, and it's somehow what I wanted to spend some time on, because it's the only rectifiability result I'm going to prove. So, let me introduce the basic object. Okay. And the basic object, the set, in some sense. Okay, so the game is we have, from now on, we have a fixed finite perimeter set in Rn. This is fixed. It will not move for the rest of the lecture. Then we have that, as we said, we take this measure. We only know, by definition, it's a measure, vector measure. So we can write it, as yesterday, by a unit vector field times a positive measure. Okay? And so this is unit vector field, and this is a positive measure. And the goal is to prove that mu is rectifiable. Okay, so it's really HD minus 1 restricted to a rectifiable set. And so one of the first things we have to do is, well, okay, find a reasonable guess for what this rectifiable set could be. Okay, so we start from a measure. There is no set yet, and we have to produce the set, and then maybe prove that what we claim is true. But first we have to produce the set, which, okay? So, and here is the definition, which is very ad hoc for finite perimeter sets. So this doesn't really fits what was told in other lectures somehow. But in every rectifiability theorem for measures, at some moment you have to construct a set. Okay. Now the way it's constructed here depends very much on the fact that we are talking about finite perimeter sets, and so the way you construct it is the following. The classical construction, at least, is that the so-called reduced boundary of E is the set okay, I use the usual symbol for the boundary, except I put a star here, which reminds me this is not really the boundary. In fact, it's a subset of the boundary, and is the subset of all x in the boundary, if you want, with the following property, such that if I take this vector measure and I take the density with respect to its total variation with respect to mu, it exists and has a vector of density 1. So the Radon-Nikodym density. Here is the classical definition. Of this vector measure with respect to its positive part at x. So this is a measure, this is the other measure, exists and is a unit vector. Well, okay, but what does it mean? If we write a measure like this, we are simply saying that this vector here admits an approximate limit at x with respect to the measure mu. And the approximate limit will have. So this condition So this is the condition. I'm translating this condition here. Eta has approximate admits, sorry, an approximate limit at x with respect to mu. That's what I'm saying. Now, of course, just a second to make it clear, if you forget about the NL1 function, Lebesgue theorem says the approximate limit exists almost everywhere and agrees with the function. So now I want to make it very precise. I'm interested in the points where the approximate limit exists. I'm not requiring, because otherwise I would make a mess out of it, that it agrees with the values of eta. So what I might want to do is to change the value of eta in such a way that it agrees with its approximate limit. Okay? So, but you have to be precise about this, but okay, once you are aware that, so in some sense, since I'm interested in all points, okay, I don't want to discharge any of these points. Okay? So if you change, did I say something stupid? Maybe that's not at all necessary.
I'm not sure.
It's needed.
When mu is void, then you have a lot of approximate limits. So you want to take it only at sort of points of density mu or some kind of support of mu.
Yeah, no, that has to be in the support of mu, of course. It's okay. Sorry. No, I said something that is eta is approximately. Sorry. Continuous at x. Forget what I said before. It was a consideration which was wrong. So this means that if I do this on the ball of center x and radius r, and I take the average, this goes to 0. okay, as r goes to 0. So it's the L1 approximate continuity with respect to the measure mu, okay? Okay.
Why do we have to add that is a unit vector?
Well, because this is the I wrote down here the original definition you find in books. It will be automatically a unit vector, okay? Because, but okay, let me be, I mean, there is one point in some sense. What people wanted to do with this definition, which, okay, what the Giorgi wanted to do, because it's his definition, is to find a set, which is, he wanted to find a very precise set. So it was not to be defined up to null sets or blah, blah, blah. He wanted really a set, given the set E, this should be a set which is defined not up to null sets of any type. So he gave a very precise definition because of this reason. So it didn't, in some sense, it's not quite that definition unless you change nu in a null set in such a way that its value agrees with the approximate limit where it exists. It doesn't matter in the following, but for him it was important. I mean, it was, this result goes back to the late 50s. People didn't felt comfortable at all with this almost everywhere kind of equivalence at that time. So in some sense, he really wanted to give a very precise set. And the very precise set shouldn't be something that, you know, you don't know whether a point is there or not because it depends on which class, blah, blah. So this statement says this density exists and is a unit vector. It has to be a unit vector almost everywhere. But it's not. So he said, okay, which point do I take exactly? Those where it is a unit vector. And it exists. So here I'm cheating a little bit, because if I change this in a null set, mu null set, then I'm changing the set, okay? So let's say that to stick to this definition, what I would have to do here before is that, okay, I take nu, I replace it with its approximate limit in every point where it exists. And it has norm 1. Okay, and then, because originally nu was an L1 function, nothing more. Okay, nu by definition, eta. Eta is by definition the density of this vector measure with respect to its total variation. It's just an L1 function. It's not a function. It's an equivalence class. Well, the guy wanted to take out a set, not an equivalence class of sets. So the precise definition is this one to make it work exactly, but it doesn't matter in the rest of the theory. That's somehow the... No, I mean, I'm saying that this was the right definition. Exactly. Exactly. No, in this business you have, I mean, you cannot play too much with null sets, okay? You don't want to do it because that gives you troubles. So he wanted a set which is precisely defined. So you see, I mean, once you define this as a Radon-Nikodym of this with respect to this, it will have modulus 1 almost everywhere, but almost everywhere, okay? So, of course, then you prove that if the approximate limit exists, it has to be norm 1. But the definition was written like this. Okay, we replace it by this. Okay? Now, let me tell you.
To understand this more clearly to me, so that box does not depend on the representative of eta, but that textual efficient depends on the
This one depends. So if you really want to get the original definition, which would differ, okay, so the sets of the X such that this exists and this one may differ by a set of measure mu0. If you want to really get these sets exactly, you have to modify eta in a null set in such a way that it agrees with its approximate limit, which is sometimes done automatically, okay? I mean, that wouldn't be the first time you've seen this, that you replace an L1 function with its approximate value when it exists. Okay, you take the so-called precise representative of the, okay? So in some sense, but the fact is that really doesn't matter for the theorem we are going to prove once we have proved it, as she pointed out. If you have not yet proved it, you might imagine that it matters. It doesn't in the end, but okay. So, okay, let me tell you, why are we choosing these points? Why is this set relevant? Well, in some sense, picture your finite perimeter sets. We know it's just heuristic, this one. It doesn't work, but picture it as a set which is piecewise which is piecewise regular. Then in some sense, the point we are taking will exclude this cusp point. Okay? So what would be the reduced boundary here? So the smooth points are reduced boundary, because what is the eta here? Well, in some sense, because eta here is continuous, right? So it's approximately continuous as well. But you exclude, for instance, this point, because eta here would be this, but then you would have a transition from this. So it's clear that at this point there is no approximate limit. Not only there is no limit, there is no approximate limit, because close by you have the value of eta are in two cones, and they are well represented both. I mean, okay, so the amount of, so there is no approximate value. Okay, approximate value means, doesn't mean continuity. Sorry, approximate continuity doesn't mean continuity, but certainly this is not a point of approximate continuity of this vector field. Okay, not only is not a point of continuity, but not even of approximate continuity. We are excluding this point as well. We would also exclude this point here, because when you look here, sorry, eta is the inner, excuse me, is the inner. Remember, eta is the inner normal, okay? See, well, okay. This is the interior, this is the interior. So this point you exclude, because again, here you have that eta takes two different values far away in same proportion, so there cannot be any approximate limit. So essentially you are somehow selecting the smooth, the best approximation of smooth points of this measure. I mean, it's not, there is no such a picture yet, but this, the idea behind this definition, you can get thinking about this picture. You are trying to take away the bad points and select the good ones and hope that it works. Okay? Now, just one quick word. Here is a mu, and let's say it doesn't come from a finite perimeter set, and you are trying to prove it's rectifiable. That's somehow it's the one of the theme in Tatana's lectures. And then somehow the point is, even there you would have a problem, right? You start from a measure, you have all this density property, but at some moment you would need to produce a set that supports the measure when you want to prove it's rectifiable. And so even there you would have the problem of selecting a set which is a good candidate for supporting the measure. And then, okay, you might imagine what would be the right set in that case, for instance. Okay, so let's say you have proved that your measure has a unique tangent measure, flat tangent measure, well, unique up to constant, at almost every point. Well, then you take exactly as a support set. You would take exactly the x where this happens. Okay, that would be the set you want to use. When you want to prove that mu is rectifiable, you will choose this set and prove this set is rectifiable, and that mu lives on this set. Okay, so that's somehow, at some moment you have to do this operation. You start from a measure, you want to find out a set. So here it's done in a different way, but in the end it's the same operation. Okay, for a general measure mu with unique tangent, flat tangent space tangent measure, you would select exactly the points where this happens, but here we are very much doing the same. Okay, if you think about what this measure should be, we are exactly selecting the part where the blow up of this measure is flat. In fact, that's what the proof does. We are going to show that the blow up of the measure mu at these points is flat. Okay, that's the first step. So we, in some sense, if you have the impression that this proof that is going to follow is very similar to something that you have already heard in the previous lecture, it's exactly so.
So are there like higher codimension version of the?
No, this is codimension 1 because finite perimeter sets are codimension 1. Okay, so this is a very limited theory. It works only in codimension 1. But some of, okay, you will see. Now let me give just a second. So we introduced this set, and now let me give the main theorem and then we take a break, and then I prove the theorem, and that's it for today. Okay, so let me put the definition of a reduced boundary here. Okay. Eta is up continuous, is approximately continuous x. That is okay. And now the structure theorem here comes. Okay, let's say good. Okay, the first statement is that the reduced boundary, well, there is a zero statement. It's that the reduced boundary covers mu almost all of the space. Well, that's because of Lebesgue theorem says that approximate continuity occurs mu almost everywhere. Okay, so the complement of the reduced boundary is negligible with respect to mu. So this is zero because in some sense it's Lebesgue theorem, which says that approximate continuity occurs mu almost everywhere. So mu is concentrated on the reduced boundary. Okay? Not supported, as someone pointed out, because a reduced boundary is by no means a closed set. Okay? So the example we showed before, it's clearly not a closed set, even in those examples. Okay, then let's start with the interesting statement. The first one is that this set is rectifiable. The second one, is that, yeah, the measure mu is the restriction of n minus 1 to this set. And so the derivative of the characteristic function of E is really eta times, has a structure which is very similar to that of smooth sets. Okay, except you have to replace the boundary with the reduced boundary. Okay, but then I want to be more precise. Now, in the classical case, a smooth case, this would be the inner normal of the set. Maybe even here we have something like that, and that's exactly the next statement, which says that this here is in some sense the inner normal to the set E. And how do I state that? Well, first, eta of x is normal to the tangent of the reduced boundary, which we defined 2 lectures ago, I think. Of course, this is not true at every point, but it's well, no, actually, it's true at every point of the of this. Well, but let's be not too ambitious. Okay, and then the fourth. Okay, so far we are saying that this is the normal in the sense we would expect is normal to the set, but now I want to say it's the inner normal to the set E, not just the normal to the. So you see, as far as we know, this reduced boundary in D could have a geometry which is not unrelated. Now I'm saying that they are related. Okay, so not only this normal, this vector field eta is normal to the tangent, but it's also the inner normal to the set. And how do I show that? I take my favorite blow up, as yesterday, and I claim that they converge, well, to what? To an half space. Which half space? The one defined by eta of x. As usual, convergence in a one of sets is understood. In L1 lock, sorry, that was stupid. Of course, I mean, you have to be careful because it's a convergence in Rn. Okay. So basically what I'm saying is that the picture is the following. Here is the tangent to the reduced boundary, which exists as a rectifiable set. This is the point x. Well, actually, this is the tangent, well, translated to x, okay, so centered at x. Then here you will have your finite perimeter, set E. Maybe be some crazy pieces even here and there. But I'm saying that as if you look closer and closer to here, and you enlarge this, then this will converge to this. You will get closer and closer. So here, once you enlarge, this point x is taken to 0. Okay, and here you have EXR. Gets closer and closer to this half space, the upper half space, okay? So now, eta of x became the inner normal in, well, in geometric, not just in some abstract meaning, but in a very geometric one. I mean, it's really the inner normal, okay? Well, let's go on. I think that to make place for the other statements which I want to keep, I have to delete this. Okay, let's see if I can fit them there. Then a corollary of this picture, if you want, is that when you look at the density of E at a point of the reduced boundary, you get 1/2. Actually, you get more, right? I mean, this you get, but in particular, you get 1/2. Well, this is true at every x in the reduced boundary. And this was true, sorry, at every x. Also, in the okay. I don't need to throw away small sets, null sets. This is really true pointwise. Well, okay, sorry. Okay, right. This would be eta of x. That's defined as the approximate limit in the point x. Now, this is equal to the tangent almost everywhere. For that, yes, to identify this normal space. So this is the normal, the orthogonal, okay? Now, if I want to write this equal to the tangent to the rectifiable set, he's completely correct. That's only true almost everywhere.
That feature does not imply that plane is tangent.
Hmm?
I just got, maybe I forgot the definition of tangent, but that line, that plane,
Yeah.
looks like the tangent.
It's for counterexample. So the small pieces you draw there may have a large boundary and small area.
Yeah, but then you are not in the point of the reduced boundary.
Yes, this is the question.
Yeah. So in fact, I think it is. I think it is the tangent. Sorry. Okay. Wait. There is a problem. He is right. This is all correct. The question is whether this is true for every x or only for almost every. Perhaps for almost every x. Okay. I think not, but now I'm not 100% sure. Okay, because I was thinking of this all the time. Then I said, oh, let's call it tangent, but I didn't check it's the tangent, except it must be the tangent almost everywhere. So he's completely right. At the moment, I don't know. I guess it's the tangent at every point of the reduced boundary, but let's go slow. Maybe you are right.
You have counterexample on the board.
No. Let's discuss that in the break. Okay, and then the last one is that, which completes the picture. Take the point of density S of E. The x such that E has density S at x. Okay, and S is between 0 and 1. And then what comes out is, okay, so we found out that in the reduced boundary, the density is 1/2, as we would expect. We know that all of the bound, in some sense, that's the real part of the real boundary of this finite perimeter set. What happens in the remaining points of the set? You would expect, I mean, in the case of a smooth set, the density is either 1 or 0 or 1/2, and 1 are the interior points, 0 are the exterior points, and 1/2 is the boundary. And here is very much the same. Then, if you take the point of density 1, take the point of density 0, take the point of density 1/2, or if you wanted the reduced boundary, which is for the statement is more or less the same, then this is not the entire space, but it's almost all of the entire space. Okay, so the remaining set is H1 null. So this cover Hn minus 1, almost all of Rn. Okay, so the behavior of the set is that in some sense up to an Hn minus 1 null set, where we don't know what happens, the behavior of the set is that if you have either density 0 or 1/2 or 1. The point of density 1/2 characterize the support of the boundary measure, the reduced boundary. And so in the rest, you have only 1 and 0, interior and exterior. Is that new? Well, actually, no. If you think about Sobolev function, you know that Sobolev function can be specified, are defined as function in LP, defined almost everywhere. But one of the first fine properties of Sobolev function is that they can be specified up to a set of capacity, of null capacity. And this null capacity gives you a dimension which is lower. And if you go and check, okay, W, 1p Sobolev function, the capacity, null capacity means something of dimension less than n minus 1. But for p equal 1, which is Sobolev, which is BV, you get that the capacity null is exactly Hn minus 1 null. So this is not really new, okay? You have already seen it if you have studied fine properties of Sobolev function. The fact that you can specify them in a more finer way than just almost everywhere. Well, but that's somehow what you expect, right? There is a gain in passing from LP to Sobolev. This derivative gives you something more. And this is the type of result which is there. Now, Wow. I don't know what to do. There is, okay, let me make a remark and then we make a break anyhow, even though I will have. So the remark is that about names, this is actually what this is the Georgi rectifiability. Okay? And the rest you put together, many people contributed to it. Okay, so it's hard to find out. It may not be stated all in the Georgi's paper. I think it's not. If I remember correctly, it's not. There is one nice thing I wanted to point out, though. This was definitely not in the Georgi's paper, and if you want, sometimes this is attributed to Federer, but what really Federer did, which is impressive, is another theorem, which says finite perimeter sets are exactly characterized as the sets where the complement of E1 and E0, so the set of points where the density is neither 1 nor 0 or doesn't exist, is Hn minus 1 finite. Okay, that's definitely Federer's theorem. So he said that looking at the point of density will tells you whether where the density is neither 1 nor 0 tells you if a set is finite perimeter. Okay, but that theorem is, I think, harder than many other theorems that I've seen in this area. It's the only one I could never figure out a proof by myself. These are easy in comparison. Okay, so that's what is known as somehow. This theorem is attributed to the Georges and Federer. It's not clear who really did what, and certainly many of these pieces were in none of their papers. But there is this part which is very nice, which says, well, these finite perimeter sets are exactly characterized as those sets where the density, where the set of points of density neither 1 nor 0 is Hn minus 1 finite. Okay. And so one direction is proved here, but this is the easy direction. Finite perimeter gives you that this set is an Hn minus 1 finite, but the other direction is the non-trivial one. Show that if you have that sort of pointwise property, then the set has finite perimeter. That's
Sorry, do you mind repeating that?
so the hard part is proving the following. You have a set E such that the set of points where the density is neither 0 nor 1 or doesn't exist
With respect to Hn minus 1?
with respect, no, the density is Lebesgue density. This is Lebesgue density, okay? It's density of a set meaning volume.
Oh, okay.
Sorry. This is Lebesgue density, okay? Density with respect to Lebesgue measure. Org.
You're talking about the measure theoretic bound.
Yeah. So what he said is take the set of points where the so-called measure theoretic boundary is the set of points where the density is neither 1 nor 0, where density is Lebesgue density, okay, with respect to Lebesgue measure. Then you measure this and you find out that it is Hn minus 1 finite, then the set has finite perimeter. That's definitely Federer's theorem. And it's, I would say, the hardest theorem around. So, I mean, I'm awfully late. 10 minutes left. I don't know what to do, honestly, because starting the...
You should speak for 5 minutes and then...
Okay, so why don't I try to start? Yeah, okay. I mean, so far, I mean, I'm sorry about that, but it took more time than I expected. Okay, so I will start. Okay, so this is the big theorem, okay, that we've. And I will start. Okay, there is something I can do. I can start telling you what is the first property. Okay, I can do some preparatory work, which makes sense. So, till this evening, I mean. And the preparatory work is this. So, we set out to prove this. It's not a short proof, but the preparatory work is the following. So there is the first set is. So we fixed a point in the reduced boundary. Now we work with this fixed. And actually it will be 0, okay, for convenience. And then the first things we show is that we start proving some property about the measure mu. For instance, in some sense these properties are not new. If you look at okay, now I'm focusing on the point 0, okay? So the ball is centered in 0. Then the first thing you want to show is that this is less or equal. This grows at most like Rn minus 1. So the goal in the end is to prove that mu is n minus 1 rectifiable. So what you expect is that it has density, n minus 1 dimensional density, 1. But we show, we show first that it has upper density bounded. And this is universal constant, as all see in the proof. Okay? So we are getting close to something that we would like to expect. And so the proof is the following. Consider this set, and you intersect with the ball of radius r. Okay? And my claim is that the derivative, so here is 0, here is r, and I claim that in some sense the geometric idea is what's the boundary of this will be the boundary of E inside B plus the boundary of B inside E. Well, but that's geometric. Let me write an identity which is true for finite perimeter set. So, but this identity is just translating the fact that the boundary of this set is given by the boundary of E inside the ball and the boundary of the ball inside E. Okay, but it's written like this. The derivative of this truncated set is the characteristic function of B multiplied by the derivative, the boundary of E. So that's the measured derivative of E, and that's the part of it which is inside B, plus, well, the converse. Okay? The part of the derivative, measured derivative of the ball, which is inside E. This is not true for every R, because there exactly it happens that we are working with finite perimeter set. This is true for almost every R. Okay? Otherwise, you might be in troubles. All these objects are well defined, but the identity is not. And okay, how do you prove it? Well, it's true for smooth sets by geometric reason. And then you use the fact that smooth sets approximate finite perimeter set to show that this identity passes to the limit. And where do you really have to use why the almost everywhere appears, almost every R, is because the approximation of a finite perimeter set with smooth sets we said is in L1. In L1 of the plane means that if I restrict my sets to a sphere, they may not converge. Well, but they must converge by Fubini on almost all spheres. So that's where the convergence fails you if you fix R. But if you take almost every R, you are okay. Okay, so it's a technical fact, but it's not complicated. Okay, then for this R, okay. And now, and then now you do the following. So now I'm saying we are really working on on a point of the reduced boundary. So here is 0 is a point of the reduced boundary, and this is R. And I'm trying to say that since my boundary is all directed like this is the assumption about the reduced boundary. The direction of the normal here is in exactly one. So the point about this statement, the non-obvious point is why there should be, in some sense, in a ball, you can pack as much boundary as you want. I mean, you make a very convoluted set inside here, then you have a huge measured derivative. How comes we have this bound? Well, it comes out of the fact that, in some sense, geometrically, the fact that I'm in the reduced boundary means that this normal is only goes up. So I cannot put inside this ball something which is a lot of boundary, because to do that, some of the boundary will point down. Okay, so this statement is true because in some sense my boundary cannot go around. It has to be only directed upward. So I mean, in some sense, if I want to put more boundary, how do I do that? You know, you would like to do something like this. But this has boundary up and boundary down as well. So it cannot happen in a point where the normal is approximately continuous. Right? That's the idea. Okay, that's why you start getting some nice properties out of the definition of reduced boundary. The proof, although it's technical, because you cannot appeal to this geometric intuition, and the way you prove it is you simply integrate a constant vector field eta 0. Okay, so you integrate this with respect to the measured derivative of this set. Now, by definition of finite perimeter sets, well, this has to be the integral of the divergence of eta 0 on E intersected by R. Oh, but this is 0 because eta 0 is constant, so the divergence is 0. Okay, so I'm integrating a constant vector field, its divergence is 0. And then what you get is, well, okay, now we use this formula for the measured derivative, and we split this integral in two. So in some sense, the integral on the boundary of E inside BR. And we use the fact that there the measure is eta times mu, plus the integral on the boundary of the ball inside E. Oh, the boundary of the ball, though, the ball is regular, so when I think about the measured derivative of the boundary of the ball is the usual thing. Okay, so that's the smooth case. So this is just integrating this one, and here I get eta 0 times the inner normal of the ball. Okay? So these two are equal. The sum of these two is 0, so these two are opposite value. So inner normal to the ball. Well, this scalar product is at most 1. So this is less or equal than the measure of this set. On the other hand, since we are at a continuity point of eta x, well, this product is essentially 1. And the smaller I get r, the closer I get to 1. So in the end, as r goes to 0, this should converge to the measure of the ball. But certainly for r sufficiently small, is larger than half of the measure of the ball. Okay? So I'm saying that this, because of the assumption because of the fact that this function is approximate continuous 0, this is convergent to 1 in the approximate sense. but then this integral is convergent to the measure of the ball. And so it's larger than half the measure of the ball for r sufficiently small. Okay, so this is the first things we have. And now it's time to stop, I think. Okay, yeah, it's over time. So sorry for the fact that there was no break. Thank you.